once again. We're at AntennaFest 2025, and I'm here to introduce our next speaker. This is Cory Edwards from Dielectric. Cory has steadily taken on roles of increasing responsibility from manufacturing in this 25 plus years with Dielectric, transitioning from planning, purchasing, and product management roles to his current sales manager position. Leveraging this rich, varied experience, Cory now promotes Dielectric's innovative RF transmission products spanning digital TV, FM radio, low-power TV, and translators, primarily to the US and Southeast Asian markets. He also manages the company's OEM and distribution partner relationships. Cory, the stage is yours.
Thank you. So I'm going to talk a little bit about a project that we're just finishing up out in Salt Lake City for Bonneville. It's at Farnsworth Peak, which is a pretty harsh environment, pretty cool location for anybody that's seen it. A lot of TV up there, FM. And so I'm going to talk right from the beginning to the end that we've taken this project on, talk a little bit about the proposal, some of the stuff that we offered, why they might have chose what they did. Then a service contract that we did for them to help move things along. And then antenna selection, the combiner selection, go over the technology that's there kind of in depth, talk about the RFHAWKEYE. Would have liked to have shown a live demo of the RFHAWKEYE, but I can talk why that's not happening now. And then some final results. So talk about antenna options. Nick did a great job walking through, the panel antennas, ring style, showing that. There's going to be a lot of duplication here, but it'll be of the dielectric helices. And then the combiner options that we also went through with them. So as everybody knows, projects as they go on, they change, they morph. Originally, what we were asked about doing was 18 channels going into a main antenna, possibly doing a backup antenna. And so one of the things that we had proposed on the antenna front is a pretty standard 10-layer, 3-around panel antenna. This one was a little unique for us because when we had done panel antennas before, we always did them with cable fed, so power dividers, cables feeding into the back of the panels. And in this case, we were going to offer a rigid feed system, which I'll show some of that detail here of what we were going to do. These were going to be full wavelength panels, which get them about 8% more efficiency out of the system. And then, as Nick mentioned, hybrids on the back of the panels, so you were feeding 2 inputs. One thing I probably should have mentioned is we were looking at doing a right-hand, left-hand on the 2 inputs. So we were going to feed certain frequencies into one input, certain frequencies in the other input, which I'll get into when we talk about the combiner. What was interesting about the feed system is we were going to do it on rails. So each face was going to have a rail of power dividers fed in series with T's. And then we were going to put flex sections between the T's, which you can see that being pointed at here in the diagram. And the reason for that was for tolerancing on the mast and also make it easier during assembly and if something was to happen on site, easy to take apart. This had a pretty good circularity. I actually show the RMS directivity just so you can see what it would have been in peak, which was 10.6. In this case, we were doing 25 kilowatt ERPs, and they were looking to have TPOs right around 5 to 6 kilowatts was what they had gone into it with. And this would have been fed with 2 transmission lines going up the tower to feed the 2 different frequency ranges. The other thing that we offered to them was a typical ring style. So with the ring style, we were going to do what we call our optimum gain. Now we're calling it our RingMaster that's being patent pending. It would have been a fully rigid feed system as well, just like the panel, except it would have been side mounted. And we had done quite a few pattern results using HFSS as what that pattern would look like. And the nice part about this was it would have actually been a really nice 50-50 ratio on the polarization, where with the panel, it would have been a little skewed. So we showed them this pattern that we had done. We actually optimized this on I think that was a 3-foot face. is what they originally were talking about doing up there. But as you can see, the directivity is actually lower because it's more circular than actually the panel. Just the V-pole would have been more directionalized, which was going to fit exactly what they were looking to do because they wanted to cover more in the south eventually, because that's where the population was growing. We were actually going to do two antennas, two 12-bay stacked. They were going to be dual center feds. So as I talk about bandwidth in a little bit, instead of feeding a normal 12-bay 6/6, you start losing bandwidth because of the 6 being in one array. So we would have fed 3/3 and then 3/3 and then combined those. And you would have had two 12-bay antennas with different frequencies going into each array, which we've done several times. It's using some of the right-hand, left-hand polarization technique, like what you would do for IBOC, but you just do it for analog, both being analog signals. We showed them different patterns that we had done, 10-foot face, 6-foot face, 4-foot face. Again, this was just on unique towers that we had done them on. We then, as we got the order, of course, had to do the pattern work to optimize theirs on their size tower with their transmission lines. Just like Nick said, you take everything into account. So on the combiner, we were going to do a left-hand, right-hand combiner, trying to get the frequencies so that they were further away. So if you didn't do that, you had 800 kilohertz spacing, which you can do, and we ended up doing. But in this case, we were trying to get it so we could do 4-pole filters easily without having to try to skew the mass or anything like that. So we would have fed one into the left-hand side of the elements, and then one into the right-hand on the panel, and then one would have went into one antenna versus the other antenna on the slot. I mean the ring. They were worried about space, so we had given them all kinds of different layouts, just showing the manifold combiners kind of intertwined here. Another one where they were actually stacked so that the spine was all on the same side. And then in this case, you can also see that we were trying to stagger the heights, again, to do with delay line lengths, which I'll get into. And then another layout here. And this being one of the final layouts that we offered, which we'll talk about the manifold combiners and the trombone sections and how those get determined. So we get the order, it's awarded in a light phrase, I guess, because they didn't really know exactly what they wanted. They picked the RingMaster antenna. They knew they wanted that. And they ended up wanting only single line run, reconfigurable manifold, because they might want to change things in the future. They ordered the HAWKEYE. They actually asked us to do the installation. So we had to partner with a company to do the installation and then also the install of the combiner. And they actually selected 13 channels and decided this was going to become an aux. So they broke out their project into phases. Phase A was going to be to do an aux. Phase B was do a bunch of work in the building. And then phase C was going to be replace the antenna that they have there today as the main. And they were going to look at a different technology that we were proposing for that, which is our Ring 360, which if anybody has questions or you've heard about that, I'm happy to answer, but it didn't really fall in this presentation. So then the work really begins, right? You start asking questions. Hey, have you guys done a structural? What code are you using on your mounting, on your tower? Have no idea. Okay, do you have any detailed tower drawings? No, we don't have any drawings. We don't have any stuff. The guy that used to run the site left. Typical things you start here, and it becomes a common theme. And then, okay, well, on the combiner, what about the building? Where are you looking to put it? Well, we're not really sure. So basically, we ended up doing a service contract for them, which it really pulled the project together. Basically, we ended up hiring a company to go out and do tower mapping. They mapped the towers, did all the drawings of the towers. So now they have that information. When they did that, then we had to go get a structural done for them, which then the antenna passed the structural. Thank goodness, after you get $1 million contract, it did pass. And then on the building dimensions, again, they had like 3 or 4 different spots. We ended up hiring David Sanford. I don't know if you guys know him, but he does a great job. Came in, took all the measurements, and kind of helped fit where this was going to go in the room the best. So now just get a little bit behind the science of some of the options that they selected. So the RingMaster technique. So basically when it comes to ring style antennas, you have 3 options. You have the full wave, which I think everybody's pretty familiar with. Half wave, which again can be for a couple reasons. One, you can do it for bandwidth. You can also do it for downward radiation characteristics. And then you have the short spaced antennas, N-1, and you can do a combination of those. And then in the short spaced antenna, you can do that a couple of different ways. You can do it with a power divider and cables to each element, or you can do what we call an elbow style antenna, which I'll show an example of. And everything has trade-offs for it. So when you start looking at full wave antennas with our antenna, the DCRM, DCRU, DCRS, depending on what you do for powers, for peak voltage, it changes. But the circumference of that is a 36-inch diameter ring. And that's basically where you're getting the bulk of your bandwidth out of that antenna. And you end up with about 3.9, I would say 3 megahertz of bandwidth out of a standard full wave antenna. And it's just your pure function of the volume of that bay. And so then, at one time we did the Q bay, which we still do, but we use it for low band V. But again, that was to get a bigger volume. And that one did like 6 or 7 megahertz of bandwidth just purely by its size. The other way that you can achieve bandwidth is by half wave spacing. So when you half wave space, you get two benefits. One is the bays are fed out of phase. That's why you turn one tap point one way, one tap point the other. And then secondly, you get the mutual coupling, which then that all looks like volume. And so in a half wave spaced array, we can get, if without dual center feeding, you can get about 6 or 7 megahertz of bandwidth. If you start dual center feeding it, breaking it up into the smaller chunks, like I mentioned, you can actually get the full FM band doing half wave spaced array. And then, like I mentioned, you can do the N-1, which gets a little bit of a benefit on the downward radiation, but you don't gain that benefit on the bandwidth part. So on the bandwidth part, I'm still sitting around that 3 to 4 megahertz because I'm still using the bay and I don't have enough mutual coupling in order to spread that volume. But downward radiation characteristics are just as good similar to half wave spacing, but you get the extra gain because of it not being half wave. So when we do the N-1 or the short spaced array, we actually do it with what we call an elbow style antenna. So the line length between the elements is a full wavelength, but the spacing is short spaced. And again, you can do that in the 7/8 or the 5/8. And it all depends on the length of the elbow and all that. We've done many of those systems. Comes at a cost, because you add the 2 elbows. So if you take a typical 6-bay antenna, you're adding about 15 elbows and gets pretty pricey quickly. So when you look at all these configurations, again, there's benefits and there's pros and cons to all of it. On the full wave, you minimum the number of bays, you maximizing your gain. You get the lowest wind load because you have less elements. But you are limited in bandwidth. Like I said, you get about that 3 to 4 megahertz. And downward radiation, you don't get the characteristics of being able to null that out. So half wave spaced, again, full, you can get almost the full band, especially when you dual center feed them. Really reduces the sensitivity of the antenna, because when you start talking about how do you get bandwidth out of an antenna, a lot of times you can cross frequencies over. When you cross frequencies over, now as you put that on a tower and it changes, does it blow that trace back up? Then you have to try to wrap it back up with line below the antenna, which then can hurt your audio. So there's a lot of trade-offs and just a lot you got to think about when you're combining signals, where it's located. You know, if you're not going to put a radome or any ice protection on an antenna that's going to Michigan, crossing over frequencies, probably not the way to go, because the minute it ices up, somebody's going to lose signal. But again, so half wave spacing has become pretty natural for bandwidth, and for the downward radiation characters. The real driver on the cons is maximum of elements, right? If I'm trying to get a gain of a 6 bay, I'm at a 12 bay half wave. I've doubled the number of elements. It's quite a bit more cost to the broadcaster. Adds wind loading, of course, to your tower because you've doubled the amount of elements, and then more connections. One of the biggest things is the simpler the antenna, the less connections, the more reliable that's going to be for years of service. Then you have the N-1. Again, you can cut down the downward radiation, but then you're limited again back to bandwidth, and then the cost adder of the elbows, which can be cheaper than, of course, doing the double the amount of bays. So again, it's really what you're trying to get out of the application. Are you looking for downward radiation characteristics? Are you looking for bandwidth? Really plays a part into which way you would go. So in this situation, we basically needed a half wave spaced antenna, but we didn't want to build an 18 bay half wave spaced array because I need twice as many elements doing it that way. And then my cost goes up, my wind loading. So if I reduce my downward radiation, again, Farnsworth Peak, I should have mentioned that. The antenna is probably only off the ground, maybe 100 feet. So you got to worry about that. You got people up there all day. They take shifts. I think it's like a week on, week off. So it's always manned. And, but if I do downward radiation, you know, do I lose bandwidth? So what if there was a new technology that I was able to get my bandwidth, less bays, less wind loading in that case, which means more economical, and I was still able to reduce my downward radiation via wind? We patented, or we're in the process of patenting, the RingMaster antenna. So the RingMaster antenna uses a different concept. So basically you can take a 2 bay full wave array, or you can take a 4 bay half wavelength array, or you can do a combination of a half and a full. And I can get the same gain out of a 3 bay with the downward, with no downward radiation, like I do with the 4 bay half wave, and the same gain as a 2 bay with a 3 bay. So just walk through some of that. So basically it's all in combinations of halves and full wave wavelength arrays. And if you look at the chart over here, it's kind of interesting. When you get up to a 16 bay, there's actually over 32,000 combinations that you could do playing with that full and half wave. If you stick with pairs, so a pair half wave, full wave, pair half wave, and as you can see, we're doing that with a dual center fed here on this, the array closest to me. You're going to get the downward radiation characteristics of a half wave, but you're going to get extra gain out of the antenna because of the full wave, and we can do the whole FM band because of that. So in this example for Farnsworth Peak, it was either do an 18 bay half wave antenna. We offered a 12 bay RingMaster that wouldn't have the downward radiation characteristics. So that would have actually had the full gain of that 12 bay would have had the full gain of the 18 bay array. But in this case, because we needed downward radiation, we ended up doing one with a 12 bay RingMaster that was 80 feet long. So it came in less length than the typical half wave, got the same downward radiation characteristics, and I still got the whole FM band. But as you'll see in one of the slides here, I'll show, but you needed a little more, you needed basically a kilowatt more transmitter power. So some of these that we've installed, we did a 12 bay on this. Again, it was a dual center fed. They needed 3 channels. The 3 channels all came in under a 1-1. You can see they got the whole entire band under a 1-2, and that was the same gain as an 18 bay half wave, and it was a 12 bay antenna. Did another one in the Bahamas. This is with our C bay. Our C bay only has a 20-inch diameter ring. So as you start, again, shrinking the size of that ring, your bandwidth really changes. So normally if Dielectric was asked to do anything broadband, we always went to our DCRM model. Again, for applications that were only taking 2-3 kilowatts, it's kind of an overkill of an antenna. Now we're able to supply either our DCRC, our E, our H. You can do all different combinations. But in this case, again, they ended up with 3.8 megahertz of bandwidth, all under a 1.2. Again, if you think about this application being in the Bahamas, you could have easily just wrapped those 2 frequencies, crossed them over on the Smith chart. But the minute you got a heavy rain, typhoon, weather, you would have started to see a big change in the performance of that antenna. And by getting the whole bandwidth in, it allows that to drift and still not hurt the signal. Another thing I should just point out is I don't know if that support pole would have actually handled the DCRM. Yeah, it was quite a process. For vertical bridge, as Nick mentioned, they're putting up the panel antenna. We got the 2 aux antennas there. Again, this one they wanted a right-hand, left-hand polarized. So these are 12 bay arrays, dual center feds, 5 channels of operation, but the whole band is covered. Pretty nice VSWR. And those were the antennas set up on the back range. This was the other channels because they split them up. This is the Bonneville array, which we'll go over in a little bit, but basically this was 13 channels, ended up being a 16 bay when we were all done. They made more changes, they wanted more gain, had the low RFR. That's why we ended up with 16 versus the 12, because they wanted that gain. But as you can see, they're stacked in halves and then full waves in between them. Again, this, you've got basically the whole FM band under a 1-1 VSWR. I believe it ended up being 93 feet. 90. Yeah, I think it was 93 feet. That I don't know. I know that this one's fed with about 140 feet of line. Yeah, but I don't know the answer to, as a rule of thumb, how far they got to be. Yeah. Yeah, that's good. Yeah, very well. So we've had a lot of comments about this. A lot of the competitors are saying, "Wow, you end up with some holes in your elevation pattern." Be the first one to say absolutely correct. But out of them 32,000 combinations, you only use the ones that work. There's a lot of these that won't work because of that. And to prove that out, we actually did all of the elevation patterns and the array theory formula, and then took on top of that and actually did the HFSS measurements on them, and then overlaid. And as you can see, they actually match. Again, doing it with the pairs of half for the downward radiation characteristic as well. So in conclusion, with the RingMaster, it's kind of the best of both worlds. What I'll say is everything has a spot. So there's a lot of times I'm doing one right now. 6 bay full wave was the best option. So I mean that's what you quote. I could have easily said, oh well, we could do a 9 bay or whatever. But again, trying to get something economical to the broadcaster is the key, especially in the FM business, to win projects. Other thing is less connections, as I mentioned, that's reliability. The less connections you have, less chance of failure points. Easier installation too for the tower crews. Now I'll talk a little bit about combiners, our reconfigurable manifold. So basically about 2 years ago, really started pressing upon manifold style combining, trying to make it so it was easier, trying to take away the excuses as why you don't want one. A lot of broadcasters say, well, I don't know if I want to add a channel later. I want the flexibility. That's why I want a manifold. I mean, a CIF combiner, power handling has been thrown out. There's all kinds of reasons. So what we do now is we actually take the S2P files off of those filters as they get tuned. And at any time, if you called up, we could redo this in the simulation circuit software that we've created. And we could actually add channels. They don't have to be in any particular order. We're actually doing a project right now for Africa, 13 of these 4-channel combiners. And the way they're laid in the containers, certain people wanted their transmitters in a certain order. And so used to be you had to have from one frequency to the other. These are all jumbled, mismatched. It doesn't matter. You can overcome any of that. We also developed the short length, the shorts for each channel when we do our combiners. So if at any time you had a problem in the field, we could send you the short circuit length. You could plug it on, roll the combiner out, fix it, and everybody else is still on the air. Because that's been the other thing is hey, once somebody has a problem, now your whole thing's off the air. That's not true. The interesting thing that's going on with the combiners right now for Africa is before we always took the simulation software, we predicted the lengths, and then the guys on the floor would still go do them all manually, and then they would say, okay, this length works, this length doesn't work. But we've fine-tuned that program that right now they've tuned up all of the frequencies on the filters. So they had 4 filters that were in the test lab. They've been tuning them individually to the frequencies, and they're cutting the splines based on the software. So right now, by probably the end of this week, they'll have 8 of these splines already made, and we haven't even tuned the filters yet because we don't have them in the factory. But that's how reliable it has become with that software. So the same thing, if later you wanted to add a channel, take away a channel, change a channel, you can do the same thing. You'd have to replace some line lengths, between the elbows. But the whole point of the elbows is now your output and your input's fixed. So you don't have to change that. So all them lines stay. It's just a matter of changing the delay lengths. If you wanted to add a channel, then of course you either add it to the end or you add it to the front. The nice thing about a manifold combiner is it doesn't matter where you are in that chain, you have the same specifications. Whereas if you're in a constant impedance filter, the one that's closest to the antenna has the best spec. The one that's furthest away from the antenna has the worst spec because he goes through all them hybrids. So then one of the things that came up is power. So we took a look at what we do on some of our television stuff for power. So now what we do is we can add a power divider on the input side, split the power, which takes away the hybrid. As Nick mentioned, the hybrids become a voltage problem, especially with IBOC and with multi-channels. And we derate our hybrids by 20% of line power. So all of a sudden you put out a constant impedance, it's got 6-inch hybrids, all of a sudden it doesn't meet, you got to change out hybrids. So what we're doing is we're actually combining the inputs with a power divider, and then the only output hybrid is the final one. And then you're combining those 2 chains into one line. Again, gets rid of some of the cost. So that's one of my functions is figuring out what all this stuff costs all the time. Basically, when you look at a CIF module, the 2 filters are a cost for each filter. The hybrids basically equal the cost of a filter. So when you do a costing model, it's almost like you did 3 filters with a CIF versus just the 1 or the 2 in this application. Again, this was a layout that we did for a customer. They wanted top half, bottom half into a main and an aux, stacked them, used the power dividers so that we could handle the power, and then the hybrids on each output. So as I mentioned, we've basically modeled all of our line symmetry in HFSS. Your short circuit going into the filter, it goes into that first cavity, so that's taken into account with that spline and the line lengths. And then, of course, trying to get those line lengths as short as possible is where you gain your bandwidth on the unit itself. Again, this is just showing different applications where we've changed the spline. We actually have a video on our website that you can see it being done firsthand. They tuned it all up. They ended up changing the channel, changed all the line lengths. It's pretty cool to watch. And how they did it was they're fast forwarding through it, so it doesn't take you the whole hour and a half it took, but it's pretty impressive. But again, that spline can change a lot of different ways, but your inputs and outputs all staying in the same location. So basically, we've done the same thing on our TV line as well, and using the UHF scenarios, again, trying to leave channels in certain orders, and it all matches the same, whether it's done in waveguide, whether it's done in coax, it's all manageable. Again, the big thing's knowing the S2P files so that you can do it. So in conclusion, on the manifold combiner, we have it so now that we can do power levels as CIFs. Even though you're using manifolds, you can get the smaller footprint. You get the electrical performance, which will show you the results of the 13 channel. It's pretty impressive. And again, it's all a function. And I've had a lot of people ask me, how come it took this long? I can tell you for us, it's HFSS, because before it would have been arts and crafts. You would have had to hand make all this stuff and prove it out, and it would have took you a lifetime. But with the software, it makes it very easy to make changes and see what's going to go on. So I don't know how many of you are familiar with our RFHAWKEYE. The RFHAWKEYE consists of a PU unit and a CU unit. The CU unit is basically the brains behind the operation. There's a coupling section that goes inside the building that injects a RF signal. So if you're doing FM, basically you're using it's around channel 13, 14, I think, somewhere in there. It's a signal, and you're doing a live time domain while you're on the air. A transmission line doesn't really care what that frequency is. It's just measuring it during a time domain. So of course the antenna is gated out, so you can't look into the antenna. I mean, you can a little, but it's very limited. It's like to the first slot. But basically every one of those lines represent a flange going up a tower. And just wanted to talk, I was hoping to do a live of the HAWKEYE that was up at Bonneville. But as I mentioned earlier, things kind of changed. That antenna got put up, which I got pictures of. And then after it was put up, they decided, you know what, we're going to keep this as our main. It's no longer going to be an aux. And when they did that, then they weren't covering to the north as much as they wanted to cover. So now the antenna is being rotated based on some simulation we did. And that's actually happening this week. So unfortunately, I couldn't get into the HAWKEYE, or I'd be showing you. And what's been interesting with that HAWKEYE is that, of course, I'll have pictures of it here, but the main antenna is not very far from where this aux is. Eventually, the main goes away, but you were able to see all the signal that was shooting in, and the HAWKEYE was showing that all as reflected power. So if you couldn't see that you weren't having degradation, you'd think you were having a major problem because of all the energy that the other antenna was shooting into it. But so we do this for UHF, VHF, FM, and just to show you a couple of the success stories. So this was actually a line that had burnt up when we were actually testing the unit. We actually, Sinclair has a tower out behind our factory, and we said, hey, we'd like to go up, we'd like to test this unit. One, we had to do some work with the FCC to show that the amount of pulse that we were putting into it wasn't affecting radiation, because it had to be under a certain level. And while we were actually doing it, we said, hey, it looks like you guys are having an issue up on the tower. And they were able to pinpoint this. The resolution on this is plus or minus 2 feet. So we can tell you exactly which flange junction to open up. And they found this, and this was under power. This was broadcasting. Transmitter hadn't shown any reflected power. They thought they had a real happy system, and when they opened it up, this is what they found. So what we started noticing on this particular one is we're showing the lines. So we have what we call a warning, which then it starts sending emails, and then it has a threshold that it'll go above. And when it does that, you can actually have what we call an in-out box, and it'll tell the transmitter, hey, stop running or whatnot, or it'll do all kinds of different interlocks. So in this particular case, what we look for is we look at these dots. These dots are taken over time, and we're making sure that they're coming back, which a lot of times they do. It's pretty amazing what goes on with transmission line as it's moving on the tower, windstorms. You actually will see arcing, and you think, oh my God, there's a problem there, and it comes right back. It's pretty amazing what we've discovered with this unit. But in this particular case, you could see the dots weren't coming back. They just kept climbing and climbing. And what's hard to see is that we're only looking at like a 0.0001. So it looks pretty drastic, but if you were just looking on a network analyzer, it's not that drastic. So they opened up the line at, in this case, it was 62 feet off the ground. They found this elbow that was there that was causing, well, what we believe was causing the issue. Said, geez, you ought to take a look at that. What they found is that there was actually a tuner sitting on top of that elbow. That tuner was loose. So if you think about that, if you were at the site and you were doing a time domain measurement with your network analyzer, and this thing wasn't under power, you probably would have never even saw that was loose. But as that grew, temperature, rises, then you start to see that it's a problem and it's not coming back. But I'm not convinced that you would have seen that with a normal, just look through the network analyzer. You might have thought that it looked a little funny, but it would have, again, been like a 0.001 and might not even investigated it. Number two, it just says basically they were able to tighten that up. They replaced the bullet on the transmission line and an inner, and then they were back up and running. No damage to the rest of the system. Site number two was kind of interesting. Started getting some real high reflective power. And in this case, it was during a snowstorm icing event. And so basically they wanted somebody to come out and climb to inspect. And we said, well, look, we're looking through the HAWKEYE. We don't see any issues at all with the transmission line. So we believe it's the antenna. And we got to believe that if you just wait until that ice goes away, you're not going to have an issue. And sure enough, once the ice melted and basically all of it went away, and it saved them from sending somebody up for no reason, and probably would have cost quite a bit of money during the middle of the icing event. With this, I will say that this part of the presentation I don't care for. I almost took it out. The Apollo makes it look pretty easy. And anybody that's done this type of work, it's not very easy. To look at the trend analysis and actually see what's moving, looking at these plots all the time. We sell these units. A lot of people think, oh, once it goes above the threshold, I know I got a problem, I got to call somebody, and it's not. It's a lot of work as far as doing the analysis of this, looking through what it's been doing over time, And so this program makes it look a little simple, but basically with the Apollo program, you know, if you have multiple sites across the country, you can see them all. In this case, green is good. Yellow, there's something going on. The orange ones actually aren't installed yet. But it shows you a nice little, you know, view of your VSWR. It's a power metering, so it tells you exactly what your power is out, what your reflected power is. We were having this conversation last night, actually over dinner. You know, some of the transmitters, I go in and you see, oh, it's got 2 watts reflected. I mean, come on, everybody knows you got more than 2 watts reflected. So I do believe it's nice to have a power metering software that tells you a real number. Again, you can take the plots, you can look at all the flanges, you can blow those up, you can zoom in to each section, tell you exactly where, which stick of line it's at. When we actually put in the unit, somebody comes out, they do the time domain measurement, and that's basically setting the threshold. So you know where you started, and then, if you look at this trace here, you have the 3 at the bottom. Those are probably things that are sensitive to frequency. But as long as you know that going into it, you'll see whether they change. But like if you have on a UHF, if you have a transformer section that wasn't broadband, it was narrow banded, you'll see the spike. But that gets labeled. Everybody knows that that's a spike from the get-go because it's the transformer. It just shows some of the end results. Again, this was the data off of the antenna. I couldn't actually get the screenshot that David did when he matched it through the combiner up there. Would have been nice to have been able to show, but basically it was just a little elevated over a 1.1. Again, that had some tower effect to it. That's why. Some pictures. You can see how close the main antenna is to the aux on the picture that's the furthest over there. Again, it gets quite a bit of crosstalk. Eventually, that tower, I guess, is going to come down. Right now, it sits over the building, and one of the places that the feet are coming down is actually eroding off of the mountaintop. So that tower will eventually come down. And again, they talked about putting up a new tower, and they were going to put up a Ring 360 there. You can see some of the obstacle. The UHF aux antenna is on an opposite leg. It would have been in the same aperture. That was one of the other reasons why they decided to go with the ring versus the wraparound panel, is it saved them from having to do something with that aux. And then just some up close pictures. I will say, if you're used to looking at typical antennas on towers, I about go off the road because I'm always looking up when I go by one. It's kind of interesting when you see the ones with the pairs now of the short wave and the full wave. They look very awkward on the tower. The combiner, again, where it ended up going, this eventually is supposed to get moved when they add on to the building. This will actually get changed a little bit in layout, but to where it needed to go first, it ended up being a stacked array. One of the cool things about this, again, was each station with their losses all sitting around the same. VSWR all sitting around the same. I think this one actually shows it, shows the thing, but we basically specified a 0.65 dB loss through the spine and through all the system. All of them came in under. One of the things we were concerned about is intermods because it was 800 kilohertz space. As you can see, we actually took measurements that were only showing 600 kilohertz space. And if you took the worst one, which was a 31 dB of isolation, and then you basically doubled that, and then you added the 20 dB of loss through the transmitter, you're at an isolation of 82 dB. So all the intermods passed. I will say David Sanford was a champ. I think he ended up taking 186 measurements for the intermods. He actually did it in a pretty cool way. He filled out the chart. He actually turned on the transmitter that mattered. did all the intermods that were related with that one transmitter, went down, shut that one off, or he'd probably still be up on the mountain taking all them measurements. This was when it was in the factory. But like I said, it was a pretty impressive system. This is David in the room that it actually ended up going in to begin with. Did a very good job of installing it. Tourist actually did the installation of the antenna, did a very good job, and Grundy Telecom was actually on the top of the mountain. They were doing a new 8-inch line run feeding the Katrine UHF antenna, and they're actually going to do the rotation part of the project, which ended up just needing one new spool piece for the input, and then needed new anti-rotation brackets. Well, they're the same ones, they just had to be shortened at the angle it was going to go. That's it.
Excellent. Thank you very much, Cory. We're going to get some questions for you real quick from the audience.
Real quick one. Back at your start, all of the elevation patterns were showing 0. And Farnsworth is way the heck up there from Salt Lake City. Was that just in the design phase? And then
Yeah, that was just design. It ended up having beam tilt added to the antenna. Yeah. And believe it or not, I didn't mention that, but beam tilt will help you also with bandwidth because you end up getting that phase delay there. So a lot of times you can just take a center fed antenna, and what scares people is you think, well, I don't want too much beam tilt, and then never want upward beam tilt. But if you have a 4-bay antenna and you center feed it, the beam is so wide, even with a little bit of up tilt, you're still going to cover the area you need, and that'll also help you with bandwidth.
When you say beam tilt, you're talking all these different frequencies. Is that electrical or mechanical?
Electrical.
Electrical.
Yeah.
But how do you determine whose frequency you use?
Well, it's going to be different for each broadcaster,
Sure.
depending. So you take an average of which,
Okay.
where you want it. But yeah,
Well, that's
each
with
one would be
FM. It's
different.
fairly close together. It's not like TV, right?
Correct.
Okay. Yeah.
Yeah.
Gotcha. Yeah. That's quite a sight.
Yeah, it was a fun project.
I think David just left our site before he went there.
Anyone else? You just like to make me run.
Shots from the cheap seats, I know. So the RFHAWKEYE, that's really cool stuff. And from my way of thinking, that's like a no-brainer at any master or combined antenna situation. I'm curious as to your thoughts about how effective / cost-effective it is for a single site, a single transmitter into a single antenna.
If I was putting up an antenna with rigid line, I would put in a Hawkeye. I will say cost is going to be, by the time you're all done with it all installed, you're probably around $35,000. But to me, if you're looking at a system that should be up there, I mean, we actually just replaced the TV antenna in Quincy, Illinois that was up on the air for 75 years. If you think about that over the life expectancy of that product, it's pretty small to be able to know that you're not going to have this catastrophic failure. I mean, I'm sure Dale and Nick, they get the calls every day. Oh, need 20 inners, need this. They got tower crews unexpected. I would think it'd be pretty nice to go out and find one flange, maybe 2 flanges you got to replace a bullet at, than a whole transmission line run.
Bullet.
Yeah.
The illustration you had of just the one bullet, that they didn't know they had a problem.
Yeah.
And that could have ended up with being a fire in the whole line and possibly the antenna being gone.
Yeah, especially with solid state transmitters. I mean, I said a lot of this couldn't be done without HFSS, which I do believe, but also with the art of the new transmitters being solid state, it takes a lot of forgiveness away, but it also adds to some of these failures because you don't see the problem like you used to on an old tube transmitter. So there's plus and minuses, of course.
Cory, would you mind explaining exactly what HFSS is?
It's a high frequency simulation software. So we started using it, I don't know, quite a few years ago. I will say it's a lot of money because you have to pay per seat. but it's just, you're able to do so much with it, and you can then add on different modules, you know, that take into account temperature and all these different things. And but we use it for all of our designs. So we started using it with TV antennas. Used to be when you bought a TV antenna, you ended up getting a model that was made. So we actually modeled one layer. We called it single layer data. We had a room that had 5 or 6 anechoic chambers, had 5 or 6 people in it, and they would go in and they would do all the measurements for one slot, and then we would put it into a software. That software would predict what all the other layers got to be. And you did that with every antenna. Well, think about every model that was made, because it's all dependent on wall thickness, diameter. I mean, we had parts everywhere, and then, like I said, then we started doing modeling in HFSS. What I will say is what was really nice about being at Dielectric with that data was we were able to do it on like for like projects and see that you were actually getting the same result. If you were just doing that and you didn't have all that data behind you, you'd be kind of guessing. But again, we started using it on our FM antennas, and that's when we petitioned the FCC to change the rulemaking on directional FM antennas, because it's so much more accurate. Anybody that's ever been on a quarter scale test range, I mean, you're using electrical tinfoil tape to hold on things that are the size of welding wire, and then you're saying, okay, well, this is what you're going to have up on the tower. It would be pretty interesting to go back over a lot of them old pattern studies. Yeah.
Anybody else? Oh, got one in the back.
How much interaction do you have with the contractors for each site on a different basis?
It depends. I mean, there's quite a few of the guys that are I mean, basically they share every measurement they take with us. There's other ones that aren't as familiar with us, and we don't get a lot of interaction. But I would say that probably 90% the crews are sending in the data, pictures, all that stuff to us on a pretty regular basis of all the stuff they put up.
All right. Thank you very much, Cory.
Thank you.